announcements, and let me do those first. I wanted to get these recorded so everybody would know about it. Well, having trouble getting started here. Okay, here we go. This is a new one I did yesterday. Let's get in some sort of order here. Okay, let's start with this one. Are any of you graduating this term? Actually finishing your degree this term? Not. Do you know of anyone who is? There is, if you don't, okay. I'll put it on here just so everybody can hear. There are 2 scholarship opportunities available. I'm sure there's more, but these 2 that we received something about, and you received them because you're a student, and they went to you, so check your email. One was to UAB, a presidential scholarship to UAB, the other to UA at Tuscaloosa. Both of these have deadlines of March 1st, which is tomorrow. So I don't know if you have time to get it done by then, but you might consider giving it a shot, okay? So today will be the last day I'll be reading. Well, I'll read them tomorrow for tomorrow's classes. Okay? Here's another one. The 2018 Talent Development and Innovation in Sciences Summer Internship Application Deadline. Boy, is that a mouthful. Has been extended to Friday, March 2nd, okay? So if you do want to participate, you need to pursue this very soon because the deadline is Friday, okay? Day after tomorrow, Friday. I've got it up here if you're interested. It's here, okay? Now, this is interesting. Let's see. Let me put this one in instead. Well, where's the deadline on this one? Okay. This is a new one, so I don't know that much about it. This is the last week for you to apply to the NASA program for community college students. Okay? If it says, do you know of a community college student who dreams of having a science, technology, engineering, mathematics career? Those are called STEMs, S-T-E-M, science, technology, engineering, and math. NCAS, that's the NASA Community College Assistance Program, or I can't remember what the letters stand for. Right there, it's advertised on our wall, right above the map for the building. Gives community college STEM students an authentic NASA experience with encouragement to finish a 2-year degree or transfer to a 4-year degree, 4-year university to pursue a NASA-related field or career. There's a website you can go to and find out more information. Who is eligible to participate? U.S. citizen, at least 18 years of age, and a high school graduate, registered in a community college, registered community college student for both fall 16 and spring 17 semesters. I think that's move up a year. And have at least a cumulative 9 hours in a STEM discipline, okay? I would think with all of you being in Cal 1, you probably have that, okay? Able to commit to working with NASA starting with a 5-week online course ending with a 4-day residential experience and attending virtual meetings during the interim. There is a online information session tomorrow between 5 and 6 p.m. Now, they don't say what time zone that is. They just say 5 and 6 p.m. I don't know if that's Eastern or Central time. Okay? And there's a link how to get there. If any of you are interested, I'll gladly share this with you. The applications are due March 5th, which I think is Monday. Is that right? Yeah. At 2 p.m. Central Standard Time. So there's the eligibility. So here it is, NASA Community College Aerospace Scholars. That's what NCAS stands for. Students pay only $30 registration fee to attend the on-site experience. NASA provides all travel, lodging, and meals. Okay? Applications are due Monday. These are Central Time. These are online information sessions. The next one is tomorrow, 5 to 6 Central Time. Okay? So I'll give you the information on that if you're interested. So here's the information. If you're interested, let me know. All right, here's another one. This is not an internship type thing. This is First Call Quality Services. It's a company out of Indianapolis, Indiana. A one-stop career center. They're going to be there here at Los State Community College. It's right over here in the Mill South building. What direction is that? North of us, north of the loop here that goes around this building. They're taking applications for the job fair, and here are what they're looking for. This company, First Call Quality. Quality inspectors, they pay $11 an hour. Team leaders, $13.50 an hour. When? Tuesday, March 6th, at the One Stop Career Center, between 9 in the morning and 1 in the afternoon. Benefits are available, and applicants must have a clear background check, driver's license, high school diploma or GED, and they prefer automotive manufacturing experiences. Prefer. Not required, but preferred. You can contact Ms. Brenda Thomas, who is here on this campus, okay, or Ms. Dorothy Henry. It may be Dr. Dorothy Henry. Either one of those, if you're interested in one of those positions. All right. Math team is still meeting. Not this Friday, but most Fridays at noon. They will not be meeting this Friday because Mr. Ashley will be at the same meeting I will be up in Jasper, Alabama. So she won't be meeting this Friday. And every Monday afternoon, 3 o'clock, Birmingham West Campus, the C building, which is the science building, C100. Okay? So I can give you her email address if you're interested, her office phone number, and her office number if you're interested. Okay, I've told you about the tutoring that's available on both campuses, and frankly, I think all of you would be good tutors on either campus, so you can check that out. I'll give you more information if you need it. Now, here's sort of the bad news. Today, normally in the afternoon, 2 to 3:15, I have a class. I still have that class, okay? But today, they called a meeting that's going to be going till 4 o'clock. So I will not be available from 2 o'clock until 4 o'clock. The meeting is over here in the Ethel Hall Auditorium. I should be back here sometime after 4, okay? But I will not be in the office after 3:15, which I normally am, okay? And they're meeting us to death this week because there's another meeting that's going to go from 2 to 5 tomorrow. It'll also be over there in Ethel Hall Auditorium. I have to leave that one early because I'm supposed to be in Jasper before 6 o'clock, between 5:30 and 6. So I will have to leave that meeting by 4 o'clock. So I'll be out of the pocket from 2 for the rest of the day, because as soon as I get out of the meeting, I'm hitting the road to Jasper. All right, and none of you are graduating, but if anyone listening is graduating, there are graduation meetings Monday, March 5th at 6 p.m. on the Birmingham West Campus in the ACAP building, the first floor theater. On Tuesday, March 6th, and on this campus in Ethel Hall Auditorium right across the parking lot, that's at 1:30. And then Wednesday, they're back on the Birmingham campus again at 1:30 in the ACAP building, the theater on the first floor of the ACAP building. Okay? Questions numbers and people to contact there. All right, I've already marked the roll. No new people came in. Sorry about that. I was hoping that would get somebody here, but not yet. Okay. Now, we're doing example 4. Any questions before we get started on today? And for some reason, you know, I can't figure out these projectors. They're such pains in the neck. They require you to plug them in before they come on. Now, I don't know why they are so technically specific like that, but they just will not come on unless you plug them in. All right, so hopefully this will come on now. There. Yes, it did. I was wondering why the screen was blank. And this is McConnell, right? You in the book. Okay. So now we could play a game of bridge. Okay. 4 people. All right. Example 4. No questions? All right. Then example 4, top of page 136, chapter 2, section 2.4. It says here, find the derivative of f of x is equal to 3x, okay, 3x minus 2x squared in parentheses to the third power. Now, there's a couple of ways to do this, okay? Maybe more than a couple. Yeah, I can think of several that you could do it. How would you approach that problem? Chain rule, exactly. Applying the general power rule, it says, but that's part, we're going to do the chain rule with that, okay? How does the chain rule go?
Pull the power down.
Okay, let me get my pen. I forgot to do that. Okay, pull the power, you mean the 3? Okay, so f prime of x will be 3 times. Second? Yes, put that exactly as it is, 3x minus 2x squared. To the second power, drop a power, exactly like we do the power rule. That's why they say the general power rule. Times the derivative of what's inside. And what is the derivative of what's inside? 3 minus 4x. Perfect. Okay? Way to go. Now, just to clean it up a little bit, I might rewrite that. I mean, that's perfectly fine. In fact, I think all I would do is to take out the time sign there. If you preferred, you could mark Terrell here, okay, Terrell here, but I don't know if we want to do that, okay. And if for some reason you think it's aesthetically more pleasing to put 3 times this squared, that's fine too. Yeah, no issue with that. That is a perfectly good answer. And it's, to me, that's exactly how I would approach the problem. Okay? Now, let's get the pen activated again. All right. Well, actually, what I want to do is, everybody got that? Okay. I'm going to erase that so we can see how they did it. This is a second way. It's exactly what Harrison did, but just sort of doing an extra step here. Now, not a bad idea to think this way too, because maybe not so much in Cal 1, but when you get to Cal 2, you're going to start using what they call substitution. And this is a way to do this. So it's not a bad way. What they're doing here is taking the inner function and setting that equal to a new name, u. You don't want to use, well, you could use y. I thought y might show up there, but u. Just some other thing, not x for sure, okay? And let that be that. Now, then you could rewrite this as being this thing to the third power, right? Okay? Now, once you get that, that's the general power rule, which you use, okay? And then they go back and don't use u at all, okay? Except right up here. So they did the very same thing you did. They took the n, and it wasn't really necessary to do this, but if you wanted to, you could. N times u to the n minus 1 times u prime. That's the chain rule, okay? Well, what is n? 3. What is u to the n minus 1? That's 3x minus 2x squared to the n minus 1 would be to the second power. And then the derivative of this, all they haven't done yet is take the derivative of that. So let's see what happens when they do that. And that gives them exactly what we got. 3 times 3x minus 2x squared, drop it 1 power, and then the derivative of that is 3 minus 4x. Got it. Done. I don't think they're going to rewrite it anyway. No, that's all. Any questions? The u was not necessary unless it helps you see what's going on. If it helps you see the answer, use the u. Use the substitution there. Okay? If you can see the answer and how to do it just by looking at the power there, do it. There's no fixed thing here. You get to choose. All right. They skip examples 5 and 6, so let's us do 5 and 6. Okay? Here will be example 5. Find all the points on the graph of f of x is equal to the cube root of x squared minus 1 to the second power, for which, find the points for which f prime of x is equal to 0, and for which f prime of x does not exist. D-N-E. Okay? That's what we're looking for. All the places where that first derivative is either 0 or undefined. Does not exist. Okay? What must you do first? What would be your suggestion?
Rewrite it.
I would rewrite it. That certainly would be my choice. How would you rewrite it?
Would be 1 over x squared minus 1.
Okay, there's no 1 over anything. It's
All that to the
x squared minus 1,
squared.
okay, to the 2 over 3 power. Okay? The exponent stays in the numerator of your exponent, and the radical index goes to the denominator of the exponent. Okay? Make sense? That's what you meant, right? Exactly. Right, I thought so. Okay. Now what do we do? You've rewritten it. Are you happy? Okay.
Then we need
Now we what?
put the 2/3 out front.
Okay, we take a derivative, okay, for f prime of x, because that's what we're going to be looking for, values of f prime. So we got to take that first derivative. The question, yeah, okay, never mind. Okay, and you take the 2/3 out front, okay, x squared minus 1
-1
to the negative 1/3 power
times
times,
2.
not quite, 2x. Okay, 2x. Got it. All right. Now this one, now I will rewrite a little bit. I guess I'll go back to radical form 2. In your numerators here is a 2 and a 2x. That's all, because the 3's in the denominator, and that minus exponent puts that in the denominator. So all that's left in the numerator is 4x. Okay? And what's in the denominator is a 3. And if you wanted to, you could go back and write this as the cube root of x squared minus 1. Wait a minute. Yeah, no, got it. Okay. I looked at that and thought I botched up something there, but I think we got it right. Okay? Now, there is your first derivative. And what do we want to do with that first derivative? First set it equal to 0. That's what we're looking for. The values of x that make that first derivative equal 0. And what value of x will make that first derivative equal 0? X equals 0, exactly. If you put a 0 in here, 4 times 0 is 0, 0 over 3. Because 0 to the second power, negative 3. Okay? Who cares? As long as this is a 0 down here, because this would be a negative 1. The cube root, you can take the cube root of negative 1. If that was a square root, you cannot take the square root of negative 1, but you can take the cube root of negative 1. That would be negative 1 times 3 would be negative 3. But who cares? The numerator is 0. As long as the denominator is not 0, and negative 3 is not 0, that gives you. So the only place where you have a first derivative equals 0 is x equals 0. So it says find all the values of all the points on the graph. Okay, now a point on a graph is written how? As an ordered pair. Okay, so if you put x equals 0, x equals 0, that's the x coordinate of that point. How do you get the y coordinate of that point? Plug it in here, exactly. Because this f of x is y. Remember that? Okay? So, plug in the 0 there, and what does that give you? 0 minus 1 would be negative 1. Square it would be plus 1. The cube root of plus 1 is 1. Okay? So your y value would be 1. All right. That's the one and only place where your first derivative is 0. Are there any places where the first derivative does not exist? What would make that first derivative not exist? Yes, if x is equal to 1. Because not just 1. Negative 1 as well. Because if x is equal to 1, sure enough, you'll have a 0 in the denominator. Can't happen. That does not exist. Or if x equals negative 1. Negative 1 squared is also 1, and that doesn't exist either. Okay? So, plus 1 and negative 1. But we need points for that. So, if you put a plus 1 in, what is your y value? 0. Okay? If you put a negative 1 in for x, what do you get? You also get 0. So those are the 3 points where either that first derivative is equal to 0 or it does not exist. Okay? Make sense? Now, y'all just told me what it was. Are y'all okay with how you got it, or you want to have a little more formal way? How did you know it wouldn't exist at plus or minus 1? Oh. The denominator can't be 0, right? 3 is never 0, so just forget about that. So what we have here is the cube root of x squared minus 1 cannot equal 0, right? Well, the only way that could be 0 is if x minus 1 was equal to 0. So we could say this is x squared minus 1 cannot equal 0. Okay? Now, what could you do with x squared minus 1? What's your F word? Factor. Okay? And how does that factor? X plus 1 times x minus 1. What do we do with that? You set each one up, so x plus 1 cannot equal 0. Now, if that was an equal sign here, right there, then we say or. But with a non-equal sign, we say and. It's not just an or. X minus 1 cannot equal 0. Both of those have to hold. What do you do with the first one? Subtract 1 from both sides, and that gives you x cannot equal -1. There we go. And this one says you add 1 to both sides, and x cannot equal +1. Because the only reason I took you this far, even though you got it right, I had to sort of coax you into getting it right, because it looked like you're going to forget about the -1. If you do it this way, that guarantees you see the -1. Not just x can't equal 1, it can't equal -1 either. So usually that's a pretty safe thing to do. This does not exist where your denominator is 0. 3 is never 0, so this part of the denominator can't be 0. Well, the only way a cube root can be 0 is if what's inside the cube root is 0. So we say that thing cannot be 0, and you carry on from that. Make sense? All right. Now, I wish they showed this figure. They don't. And I sure would hate to have to graph it. But I guess, yeah, it just irritates me they don't show the figure. Most of the time they do, but this book doesn't seem to. So let me, with those in mind, let me erase everything that's here. So you remind me of those points. Okay, 0, 1, 1, 0, and -1, 0. Okay? And they do this graph. Okay? Now the first thing they do on the graph is graph the function f. Okay? Okay? I'm just going to try to, there's -1, there's 1, and there's 0, 1. Okay? I should have dropped this down so. Well, no, I don't. Okay? Now, the graph of this function looks something like this. My drawing skills leave a lot to be desired. Something like that. Sort of a messy looking W. Okay? Actually, they don't bend as much as I said they bend, but because they go up. They're not straight lines, but they look like straight lines after a while. Okay? Now, if you do the first derivatives, the first derivative was not defined at x equal -1 and not defined at x equal 1. Okay? Now, over here, the first derivative is negative. Okay? And the closer it gets to 0, the more it's approaching that vertical asymptote. So I'm going to do the first derivative in a different color. You choose a color. Blue, okay. Light blue or dark blue?
I say red.
Oh, red. I can't hear. Okay, we'll do red then. If I could get it. There we do. Okay. So the first derivative here is, it's approaching this is sort of interesting. It's approaching a value of -2. I wish I still had my thing. If we go back, let me write down f prime of x. Remind me what it was now. It was 4. Y'all got f prime? 4x over 3 times the square cube root of x squared minus 1. Okay? Now, so when x was out there less than -1, okay, I don't know if you remember this, we're graphing this now, okay? Now, what we are looking at is what's happening in the long run, okay? And that's going to be a ratio of the leading terms here. Now, this is sort of hard to see the leading term, but when x gets very, very large, here's a trick. Multiply and divide numerator and denominator by the same thing. I'm going to multiply it by 1 over x, okay, in the numerator. In the denominator, I need it to be the same thing, so I'm going to divide by 1 over the cube root of x cubed, because that's 1 over x, right? Cube root of x cubed is that. Okay, so if I did that, the numerator would just be 4, okay? The denominator would be 3, the cube root of 1 over x cubed, 1 over x, because the x squared over x cubed, okay, would be 1 over x minus 1 over x cubed, okay. Now, certainly x cannot x is going to be getting very, very large. Not going to 0, going very, very large. Well, this goes to 0 then. 1 over x, as x is very, very large, goes to 0. That goes to 0. So, yeah. No, I'm sorry. I think what I needed to do was divide by 1 over x squared. Let's just forget about it. But anyway, it's not an easy thing to do, but if you let your graphing calculator do it, it does this thing. Okay? It's approaching that vertical asymptote because here your slope is going to negative infinity, right? And it seems to be a constant there, and I was going to try to show you why it looks like it's a constant, but it's a little complicated, okay? And up here, this is a positive slope, but as it gets closer, see, this should be coming in like this. That's going to positive infinity, and it's going like that too. This is the first derivative. Now, the slope in here is positive, but decreasing, going to 0 here, okay, and then going down here. So that's your first derivative graph, okay. I really probably should have put the vertical asymptotes, because that refers to the first derivative graph, not the function. The function is the w there. It's defined everywhere. The first derivative is not defined at plus or minus 1, but it's defined everywhere else. Very negative, or negative value down here, positive going negative up there, and then negative again. Because see, this slope is positive going to 0, and then negative going to infinite. Oh, this is what they call a cusp. Anytime you have those pointed type things, those are cusps. And there you're going to an infinity in both directions. This is a positive infinity there. That's why, no, negative infinity, because the slope is negative. Okay, this is positive infinity because the slope is positive, going to 0, going to negative infinity again, going down this way, positive infinity there. So, sorry. Okay. Sneeze. Okay. Those poor people at home listening, they had no knowledge that was coming. It wasn't required for you to do the graph. I just did it because the book did, and they did show it on the slide. Okay. So, let's clear all that out of the way and move on. Any questions on that one?
Can I explain the graphs of the slope again?
Okay, of the derivative or the function?
The derivative, I mean.
The derivative. Okay. Well, you got. Are you comfortable with the function? The function here.
Yes.
We didn't plug in values, but you could. At x equals 0. My goodness, that doesn't look right. Did I say it backwards? Oh, I'm looking at the wrong function. No, I'm looking at the right one. Oh, no, that's the wrong function. I'm looking, I don't have this written anymore. Let me write it down here. I thought I had written it here, but obviously I didn't. Okay. Your f of x, yeah, okay. F of x is equal to the cube root of x squared minus 1 squared. Okay, yeah, I erased it because to draw the graph. Okay. Now, if you plug in x equals 0, you get 1, right? So there's the graph. Plug in x equals minus 1, you get 0. X equals plus 1, you get 0. If your x is less than minus 1, this thing gets much bigger. And so it's going up like that. And okay, we have Justin and Elijah. All right. Now, anyone else come into this problem? So that's the graph of this. You're okay with that? Okay. Now, how do you do the graph of this one?
Well, so I'm just saying that it'll never be less than -1 or greater than 1. This is the vertical.
Okay. 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 When we did that derivative, this is what we got. Let me erase a few things. It's just so crowded. I'm going to rewrite this somewhere else because it's interfering with my graph. Okay. And we don't need that at all. Okay. So here was our f prime. F prime of x is equal to 4x, was it, over 3 times cube root of x squared minus 1, right? And Chasten's here. All right. Has anyone else come in? Okay. Now, how we plot this, okay? What the dashed, drilled first is blue lines that I placed on the red lines there. What they represent are the places where the denominator is 0, so the function is not defined. And we did that earlier, and see it's not defined at x equals plus 1 or minus 1. So that's what those vertical asymptotes are there for. Never touch that. Can never have those values because that makes your denominator 0. Right? Okay. Now, I was going to try to show you a way to do this, but it just got really complicated. Sorry, my head's so clogged up. It sure looks like, according to their graph, this is approaching -2 here and +2 here, and I was trying to see why that's the case. That's what I was trying to show you before. And I think what they but anyway, you can plug some values in here, large negative values or large positive values, and I bet you're going to get this thing to come out close to -2 down here and +2 up there. It may not be right on the money or something like that. But that seems to be approaching some value there, just the way they drew it. What I'm more concerned with is what's happening as you get close to that. You see, you can't reach -1. What happens when you do? Well, the derivative, which is the slope of the graph, is negative here. And like I said before, if you look at the one in the book, that almost is becoming a straight line. It sure looks like one. Probably not exactly, but it's awfully close to one. And that's why this is very close to being horizontal here, because the slope of a straight line is constant. Okay? So if that's coming in at very close to a -2 slope, which the one in the book looks like it is, that's why you have a -2 for the first derivative here. But then, as you get closer to this vertical asymptote, x equals -1, the slope decreases sharply, meaning becoming much more negative. Here it was -2. Here it's becoming much more negative, until it's approaching -infinity. So that's why it takes off and goes down there. Okay? Then looking at this edge of the cusp, okay, because when they come in form like that, that's called a cusp. The derivative is not, there is no limit for that derivative there, because it's negative here, positive here, so never becomes 0. The derivative doesn't. The value is 0, but the derivative doesn't. So it starts off being very large positively. I didn't draw it very well, but very large positive, coming from positive infinity, coming down until it reaches 0 here. Still negative, a positive slope, but becoming less positive all the time, so that's why it curves out like this. Well, if you think about it, this is basically the shape of a cubic function. And of a cubic, I meant to point to this one, not that one. And this is a cube root function, which isn't going to be far off from what the cubic function is. Just usually the cubic function goes like this. This is going like that. So its slope is positive infinity here, right at -1, and then going up to 0 here, and then becoming a negative slope here, very slowly becoming negative, until it approaches +1, and then it's approaching positive infinity. So that's why this shape is like that in the middle. And then it's very steep positive here, so it's positive infinity there, slowing down until it approaches that almost straight line. And it looks to be very close to +2. Now, whether it comes out exactly +2, I can't tell. Sure looks like it on their graph, but I don't know if their scale is even right. That 2 may only be for the function scale, because I would have thought it would have been closer to 1 1/3, 4/3, but it may not be. That's what I was trying to get to, but it just got really hairy. Okay, sorry about that. Oh, man. That's what these terrible sneezes do. They loosen things up way more than I wanted it to. Yeah. All right, that's probably way more than you needed for example 5, but does that kind of answer what you were asking? Okay. All right, let's do example 6, which they also do not include on the slide sheet. Notice they do the simple ones on the slide sheet and then expect you to figure out the harder ones by yourself. All right. So here we have another function. Differentiate this function. G of t is equal to negative 7 over 2t minus 3 squared. Now, when you first look at that function, what would be the first rule to pop into your mind of how to take its derivative? Just tell me what pops into your head.
Pull the 2 up front.
Second?
Pull the 2 up front.
Pull the what out front?
The square.
Okay.
Bring it down.
But it's down in the denominator. Okay.
Move it up to the numerator.
Second?
Move the denominator up
And give it a negative exponent?
and then do the chain rule.
That's exactly how I would. I was expecting maybe someone to say, well, that looks like a quotient rule, right? Because it's a quotient. And you could certainly do the quotient rule if you wanted to. But I think I told you before I don't really care that much for quotient rule. But you can, I mean, if you love it, go for it. I would rewrite this sort of like we did before, and as I think Harrison was suggesting, minus 7, that's in the numerator already, times 2t minus 3 to the minus 2. If you bring a denominator upstairs, you negate its exponent, right? Or if you move it downstairs, you negate its exponent, right? So that's how I would go. And then how would you take the derivative?
Pull negative 2.
Yeah, chain rule. Negative 2 times would be 14 times 2t minus 3 to the
third.
second.
Negative third.
Yes, negative 3
And then that
times
2.
2, okay? Which then, that 2 makes it pretty simple. That would be 28 times 2t minus 3 to the minus 3. Or if you wanted to go back to positive exponents, it would be 28 over 2 plus 2t minus 3 to the third power. Okay, that would be its derivative. Okay? And I really like that approach better than low d high minus high d low over low low. Okay, that would be a little on the messy side, because you still got the chain rule inside your denominator, so this is far cleaner doing it this way. In fact, almost all quotient rules, but you see, when we're doing the quotient rule, we didn't have the chain rule, so we had to do the quotient rule. Now, I'll almost figure out a way to use the chain rule rather than quotient rule, unless it's so obviously quotient rule easy, then I go for it. But something like this, no, give me the chain rule anytime. Like we said, what makes a good mathematician? Being a little lazy. So go with the one that's the easiest, okay? Elijah doesn't qualify. He's a hard worker, but you can still do it, okay? All right, good deal. All right, so let's move on to the next slide, which we'll get out of the way. Simplifying derivatives. Oh, who would want to do that, okay? The next 3 examples demonstrate techniques for simplifying the raw derivatives of functions involving products, quotients, and composites. Okay? Frankly, I don't even know what they're talking about here, but I'm sure it'll make itself obvious here. So let's do example 7, which is find the derivative of, oh yeah, I think I see what they're saying. Find the derivative of f of x is equal to x squared times the square root of 1 minus x squared. What would you do first? Second? Ultimately, you will be using train rule, but what would you do?
Get rid of the radical.
Rewrite the radical is what I would suggest. X squared, parentheses,
1 minus x squared, and 1/2.
right. Okay. Yeah, I would definitely, I don't like to try to differentiate radicals. Get it into power notation and use the powers. Okay? Now, what are you going to have to use here? I'm sorry? Okay. But what rule are you going to have to use? It's a product. This times that. So you've got to use the product rule. Yeah, you will be doing exactly what you say, but think of it in terms of product rule. This thing, the x squared times that thing. Just like you were going to have to there, but just because you rewrote it doesn't remove that from the possibility. Now, there is something else you could do, and maybe the book is suggesting this. X squared is the square root of x to the 4th power. If you did that, then you could multiply x to the 4th by everything on the inside, because you'd have the same exponents out here, 1/2. So you could do it that way. Is that what the book is suggesting? I don't think so. But let's do it the way the book's suggesting, and then I'll show you that other possibility you might want to do. Okay? So let's use product rule, which we'll use the chain rule. So how does product rule go? First times the derivative of the second. So the first, I take it, is just x squared. Times the derivative of the second, what would that be? Say again? There will be a minus 2x in there. He's already doing the derivative. That's fine of the inner part. Over 2. That's going to wipe out the 2's. Okay, the 1 minus x squared to the negative 1/2. Okay, that was a little bizarre how we did it, but I was just doing by what you said. I tend to do the 1/2, like you were suggesting, 1/2 times this thing to the minus 1/2, then times what's inside, which is times the negative 2x. That would have been out here. So we did it. We did everything right. It's just the order was a little bizarre. But we got that. Okay? So that's just the first half of the problem, right? What's the second half of the product rule? Plus
1 minus x squared and 1/2.
Okay, 1 minus x squared to the 1/2 times 2x. I'm going to put it in front if that's okay. Right? All right. Now let's clean that up a little bit. And this is why they say simplifying. Okay. All right. So this is going to be a minus x cubed over 1 minus x squared to the 1/2. Okay? I'm going back to radical notation because that's where we started from. Plus the 2x times the square root of 1 minus x squared to the 1/2. Okay. Now that is a perfectly legal, legitimate answer. Okay. However, it's a little messy, right? This has a denominator, that one doesn't. So what would happen if we put this over the square root of 1 minus x squared? If we multiply the denominator by that, what must we also do? Multiply the numerator by that as well, right? Which would then be squaring that. Okay? So this will be a minus x cubed plus, I'll put the 2x here, what is the square root of 1 minus x squared squared? One minus x squared, because the square undoes the square root. Okay? Oh, that's looking fairly interesting. And this is all over your common denominator, 1 minus square root of 1 minus x squared. Okay? So let's carry that numerator another step. Minus x cubed plus 2x, I'm distributing the 2x here, minus 2x cubed, right? All over the square root of 1 minus x squared. Okay? Now, I'm going to lead off with the 2x because it's positive. And what do you other two add to? Minus 3x cubed over the square root of 1 minus x squared. Now, to me, that's a perfectly legal answer. Okay? They do one more little step, and this is what they mean by factoring out the least powers. They factor out an x, which really doesn't do much for you here, but it's okay. And that leaves you 2 minus 3x squared over the square root of 1 minus x squared. Okay? I don't know why that's any better than the previous, and it doesn't matter. If you had stopped right here, I'd probably give you most credit. Taking it and putting over the least common denominator, that is fine. This form though and that form to me are exactly equivalent. I see no advantage of taking out the x, but it's perfectly legal to do so. Now, if you were doing WebAssign, it's only looking for one answer. And basically what you have to do is guess what answer is it looking for. So, unfortunately, that's bad. Now, what I'm trying to figure out is why in the world is this little thing up here? Oh, I was showing that you were distributing. I thought, what in the world is that? Okay. Now, so let's see how they did it. Okay. They wrote it down again. Oh, what a good, clever step. Okay. And then, just like you suggested, we put it in exponential notation rather than radical notation. Okay. Then you do the product rule. The first times the root of the second plus the second times the root of the first. Okay. Just like y'all said. Okay. Derivative of the second, the x squared times 1/2 in front of 1 minus x squared to the minus 1/2, and then chain rule that with the minus 2x. Okay? On the other side, just 1 minus x squared to the 1/2, derivative of x squared is just simply 2x. Okay? Now, what they did here is simplify this. The 2 here and the 2 here divide away, leaving you an x squared times an x, but with a minus, so that would be minus x cubed. So that's where that came from, times this thing to the minus 1/2. And then here we put the 2x times this thing. Positive. Okay. Now, frankly, there's a part of me that if I were leaving it like that, then what you could do is just factor out the x from each of those terms and leave it there. That would be, I'd see nothing wrong with that actually either. Okay? But what they do here, they pull out not just the x, they also pull out a factor of x minus x squared, or 1 minus x squared to the negative 1/2. And when you pull it out of here, that gives you, to me, doing it this way is a lot more confusing than doing it going back to putting 1 over radical. That to me made it very obvious. This way, I would have to do some serious head scratching here to see what in the world they did. Okay? But what they did was legal, but pulling the x out, that's pretty obvious. This has an x cubed, so you're left with a minus x squared there. That has an x, so you pull that out. The thing that's not as obvious is this, pretty obvious here. Yeah, just pull that out, leaving you a minus x squared. And then why they put a times 1 in there, I'm not sure. It's okay to, but I wouldn't have messed up the picture with that. But what happens here, if you factor out this thing to the minus 1/2, remember factoring out is the same as dividing. So it would be this thing to the 1/2 minus a minus 1/2, which is 1/2 plus 1/2 is 1. That's what you get at. But man, that to me is a lot harder to see and to understand. Okay? Why they put the 1 in here, I'm not sure. So it would be minus x squared plus 2 minus 2x squared. That's in your numerator. Oh, and the x. Okay? And then the denominator will be the other. And that's exactly what they did. Okay, so this is the denominator, this is numerator, that's numerator when you combine like terms. And that's the answer they get. Now, I think they leave it like that, don't they? Yeah. Now, I'm going to show you that other way, and this probably isn't any better, okay? But you can write this as the square root of x to the 4th, can't you? Isn't x squared the square root of x to the 4th? And that's times the square root of 1 minus x squared. Well, now since you have both square roots there, you can multiply these together and make it the square root of x to the 4th minus x to the 6th. You see that? Okay. Now, that is what I would rewrite as x to the 4th minus x to the 6th to the 1/2 power, and now take the derivative of that. F prime would be what? 1/2
x to the 4th minus x to the 6th
to the negative 1/2 times
4x to the 3rd minus 6x to the 5th.
Got it. Okay. All right. Now,
So where's the 1 go there?
what's that?
The minus x squared and the next one down, where does
Okay. Okay. I did skip a step. Okay, let me put that step in. I put the radical, because they're both square roots, over the product of both of them. Right? And then I multiply through. X 4th times 1 is x to the 4th minus x to the 6th. Sorry.
I should figure that out.
Okay? Now, I was going to try to simplify this a little bit. First thing I'm going to do here is up here in this part. Well, I'll write it out. Okay. Both of these, that first part are denominator parts. Your numerator part would be here. Let's factor out least common, the greatest common factor. That'd be a 2x cubed, right? Times 2 minus 3x squared. By that, just factoring out the greatest common factor between these. These are numerator, these are all denominator, right? So in your numerator, factor out a 2x cubed. It gives you 2x cubed here times 2 minus 3x squared, right? Now, what's in your denominator here was a 2 times x fourth minus x to the sixth. Let me just go and put this under a square root. Okay? My lines are really ugly, aren't they? Don't agree too fast. Okay. All right, let me go on. Okay. Okay? Obviously the 2's go out, right? Now, in that denominator, it's a square root. I can factor out. In fact, I just undo what I just did up here. Okay? I write this as x cubed times 2 minus 3x squared over, factor out this is x to the fourth times 1 minus x squared, right? That just in that denominator, inside the radical, is that right? And the square root of x squared is x times the square root of 1 minus x squared. Well, I haven't been putting parentheses, so why did I put it there? I don't know. Okay? Now, what you see is you can divide out those, and you get x squared times 2 minus 3x squared over the square root of 1 minus x squared. And is that not the same thing we had? No, it's not, is it? Oh! The square root of x to the fourth is x squared, not x. Okay. Now you factor it out. Okay, got it. Yeah. If you do your math right, it comes out. Okay. Good deal. Now, I'm not saying that's any easier. Actually, I found it to be a little bit easier. But if doing those manipulations get you confused, just go with the product rule. The point is, there's more than one way to skin a cat if you don't like cats. Okay, if you like cats, don't be going around skinning them. Okay, never mind. All right. I think we already showed what the book did, right? So let's move on to example 8. Yeah, same answer. Here's example 8. How would you approach that problem? I would rewrite it. And how would that come out rewritten? Well, x times x squared plus 4 to the, say again? Only it's in the denominator, so it would be a negative 1/3. Perfect. Way to go. Okay? And now what would you do? If you're finding the derivative. They didn't tell you that's what you're doing, but simplifying the derivative of a quotient. Product rule. I like product rule better than quotient rule, so let's go with product rule. F prime of x is equal to what? X times negative 1/3 x squared plus 4 to the I think I'm stuck in a groove here. Okay.
Negative 4/3.
4/3, you're right. Subtracting 1 is the same as subtracting 3/3. Times, chain rule. Say again? Take the derivative of that. 2x. 2x. Okay. Now that's the first half of the product rule. What's the second half?
Minus.
Plus. Yes, 1. The derivative of x squared is, of x is 1, and you just write down the second one. X squared plus 4 to the minus 1/3 power. Okay. Now the problem is simplifying. Okay. So in that first grouping there, you do have a minus, you have a 2 over 3, and you have a x times x, so that would be a minus 2/3 x squared. Okay? And then if you wanted to, you could put this down in the denominator as a x squared plus 4 to the 4/3. If you drop it down there, you lose the minus sign. So that's, you can connect them all together or however. That's what that part is. Over here, it's a lot simpler. This would just be plus 1 over x squared plus 4 to the 1/3. Okay? Now, that is a 4/3 there. It's looking a lot like a 4/8. It's not, it's 4/3. Okay. Now, what I would do next, I think what they do next, is get it over common denominator. What would be your common denominator here? Yeah. Because this is inside that, right? Okay. So, this will be, and I'm going to rearrange the order too because I don't like leading off with a plus. So I'm going to put a 1. Well, I'm not going to put a 1. I'm going to get my least common denominator first. Okay? Okay, we already said that's it right there. Okay? So what do I need to do to this denominator to make it look like that one? Got to multiply by 3, right? Okay? And then you've got to multiply by something else. What would that be? X squared plus 4 to the 3/3 power. Because this is 4/3, that's 1/3, so you have to multiply by 3/3, and 3/3 is 1. So you're just going to multiply by that, which means you'll multiply the numerator by that, x squared plus 4. Does that make sense? You see what I did? That wasn't too much of a show. You don't see what I did. Okay. What I had two fractional forms here, right? Okay. This had a 3 in it, that didn't. Okay. This had this thing to the 4/3 power. This had exactly the same thing, but only to the 1/3 power. Now, before I can add fractions, I have to have the same denominator. So I need a 3 here to match the 3 here. But if I multiply this one by 3, I have to multiply the numerator by 3 as well. And the next question is, what do I have to multiply this by to make it look like that? And I have to multiply it by this thing to the 3/3, because then I can add 1/3 plus 3/3 is 4/3. Well, this to the 3/3 power is just the first one. So I multiply the denominator by this, I also must multiply the numerator by that, right? Okay? Now I'm going to swap sides, okay? And I'm going to distribute across 2. So that's going to be 3x squared, okay? And I'm going to go on and do my minus 2x squared plus 12. Okay, I did a lot of things there at once. This was already minus 2x squared. And this becomes 3x squared plus 12. So I just put that in the middle so that I have my x squared together. Okay, and that's going to be all over 3. And I'm going to go on and write this as, since you started off with that, the cube root of x squared plus 4 to the 4th power. Okay? And that would then be x squared plus 12, because 3x squared minus 2x squared is just x squared, over 3 times the cube root of x squared plus 4 to the 4th power. Now, I don't know if that's how the book leaves it, but let's see. No, they left that as a... All right. They're not being very consistent here. Most of the time, if the problem's given the radicals, I try to get back to radicals. And they've been doing that too, but the time they don't, they leave it in the answer in exponential notation, which is perfectly fine. X squared plus 12 over 3 times x squared plus 4 to the 4/3. That's how they did it, and that's exactly the same. Does that make sense? All right. Now, based on what they did last time, they're going to factor some things out, and frankly, to me, that's harder to see the common denominators. If you see the factoring out and say, oh, that's much easier than doing common denominator, do it, okay? If you understand it their way better, use their way, okay? There's nothing magical about mine. That's just how I see it better. You don't have to see it the same way I do. So let's see what they do. Okay. They change the cube root in the denominator to something to the 1/3 in the denominator, which is perfectly fine. And then they use the quotient rule. Yay, I wanted to do it that way, and y'all wouldn't let me, did you? And goodness gracious, what a pain in the neck. And that's low d high minus high d low, derivative of the denominator is 1/3 x derivative minus 2/3 times 2x over low low, which is this thing here to the 2/3 power. Square this. 2/3. Okay? Now maybe this is easier, and if you like quotient rule and you see it better, go for it. Let's see what they do next. Okay. Again, they pull this little factoring thing, which I find less than obvious. Okay. They factor out a 1/3 from here. There is no 1/3 here, so they have to make this a 3/3. So that's why you have a 3 that pops up here. Okay? So they factor out the 1/3, which introduces a 3 here. Okay? They also factor out this. Okay? Sure, I would like to do that, yeah. Which factoring out is the same as dividing. So that would be 1/3 minus a minus 2/3, which is a 1, and that's where you got this to the first power. To me, this is not intuitively obvious. To me, looking at denominators, getting least common denominator, I'm used to that. This is so easy to make mistakes here, okay? And let's see what else they did, okay? All right. Yeah. So they factored out the 1/3, putting the 3 here. They factored out this thing to the 2/3 here, which gave you this to the first power here with the 3. And then we had, this is so easy. Okay, the 2x times x, so that's the 2x squared minus 2x squared times 1, okay, because they had factored this out and brought it over here. I swear this is so easy to forget a term here. I would never recommend this way. But if you see it and it makes perfect sense for you, do it, okay? It doesn't to me, okay? Now, once this is out here, this becomes easier, just like we had before. 3x squared plus 12 minus 2x squared. 3x squared minus 2x squared is x squared plus 12. Okay. Over that times this, okay? And that's where they got their x squared plus 12. 3x squared minus 2x squared is x squared plus 12. That's your numerator. That's all that's left in the numerator. And then in your denominator, you got a 3 and then you bring this down and times that, so that gives you your 4/3. If you like this way, by all means do it, okay? To me, there's just pitfalls. Lots of places you can forget what you've factored out and where it went, what it left. To me, it's a lot easier doing the non-negatives, but that's me. Do it however you see best. All right, here's example 9 they have here. All right, here we have y is equal to 3x minus 1 over x squared plus 3 raised to the second power. And I think what they want you to do is take its derivative. So what is y prime? Now, would you do anything to that first? I don't know. Maybe not. How would you do it? There's several approaches. How would you do it?
You want to bring the x squared minus 3.
Say that again.
So you want to bring the x squared minus 3 up?
Okay. So I think he's suggesting a rewrite here of 3x minus 1 squared times x squared plus 3 to the minus 2. Is that what you're suggesting? I like that fine. Okay. Then how would you proceed on your derivative? You've now made it what rule? A product rule. Okay. So let's do it that way. And what would you have?
3x minus 1 squared.
Okay, the first times
negative 2
negative 2 times
2x.
don't take derivative yet. Oh yeah, you could. I shouldn't. Okay, you can go on and do the derivative of that if you want to. 2x times. Hey. Okay, I'm sorry.
But do you know when the next time you'll be free would be that I can come and talk to you?
Okay, after this class, which ends around 11:10, so in about 15 minutes, but I'll be up here for a short while afterwards getting things set up here
Yes,
before I
sir.
go to the office. So you could either come here or go to my office afterwards.
Yes, sir. Thank you.
Okay. What next?
Times x squared plus 3.
X squared plus what?
Plus 3
Plus 3 to the
to the negative 2.
negative 3, isn't it?
Oh, yeah.
Okay. Now, everything you did was legal. The order, you got to just keep up with that. And this is just the first half of the product rule. The first times derivative of the second. The derivative of the second was minus 2 times this thing to the minus 3 times the derivative of that term. So he just put the derivative of this thing inside. That's where you're going to wind up put it anyway. And this is minus 3. Does everybody see that? Okay, that's just chain rule of the second part. Okay? Well, what's the second part of the product rule?
Plus x squared minus 3 to the negative 2.
It's a plus 3, isn't it? Okay, x squared plus 3 to the minus 2 times 2.
So you're saying I'm getting the order wrong. I should just go ahead and write times 3x minus
Times 3x minus 1 to the first power times 3, yeah. And it doesn't, there's nothing, the 3 would have made more sense in front of that because 3 times 2 is 6. It'd be a lot easier, but it doesn't matter. As long as you see it and you understand it, you can mess with the order if you want to. It's fine. Okay? Now, let's write out what we've got here. Again, I like to get in terms of numerators and denominators. I mean, that just to me is how to see it best, rather than pulling out all sorts of things. So, what we have here, this negative 2 is in the numerator, the 2x is in the numerator, and this thing's in the numerator, the 3x minus 1 squared. So I'm going to combine those together, make it minus 4x times 3x minus 1 squared.
What makes that in the numerator?
Okay, because you have no negative exponents. That's a positive exponent, that has 1 as exponent, that has 1 as exponent. That has a negative exponent, so that's going downstairs. So everything that is positive exponents stay upstairs and combine them together, and that would be a minus 4x times this, all over that to the positive 3. Okay? Now again, this is how I see it best. X squared plus 3. But I'm a dinosaur. If you see it better another way, and you're modern, you're on top of things, that's fine. Okay? And then we have a plus over here, and what's upstairs and downstairs here?
The x squared plus 3 to the negative 2 would be downstairs.
Downstairs, only it's no longer negative 2 if you move it downstairs. X squared plus 3 squared. Okay? So what is left upstairs? 6 times 3x minus 1. Okay? Perfect. Now, written this way, it's fairly obvious to me what is your least common denominator. What is it?
X squared plus 3 to the third.
Cubed, right? So what do you need to do to make that one like this one? Multiply by another x squared plus 3. If you do the denominator, you got to do it to the numerator as well. So this would become, I'm just going to change that 2 to a 3 here. It's ugly, I know. Y'all don't like my ugliness, but live with it, okay? And I had to multiply this by x squared plus 3. Is that okay? Sleight of hand? You saw what I did? Okay. Now, I don't know what they're going to choose to do next, but here's what I would suggest. If you're going, okay, number one, I'm going to flip terms because I like to start with the positive and have the negative at the end. Okay. Now look at those numerators, and I see a common factor of 2 here and here. Okay. Okay. So I'm going to flip sides at the same time. So we're going to have a 2. And I see a common factor of 3x minus 1. Right? Now what does that leave us with? The one that was to the right, I'm now putting first. That's going to be a 3. I pulled out the 3x minus 1 times x squared plus 3. Okay, this is probably a weird way to do it. And then we had our minus here, 2x, because all we factored out was a 2, so that left us minus 2x. And we got one of those 3x minus 1s out. That leaves us one more, 3x minus 1. And I should not have closed this. Should have included that there. So I think I have done that. And this is all over x squared plus 3 cubed. Okay? Now, I don't know. Let's just combine these together. 6x minus 2 times, this will be a 3x squared plus 9 minus 6x squared plus 2x. Did I do that right? I think so. All over x squared plus 3 cubed. Okay. Now let's simplify that inside the bracket. That would be a, I guess I don't like leading with a minus, but let's do it. 6x minus 2 times a negative 3x squared plus 2x plus 9 over x squared plus 3 cubed. Okay? Now, there's really no advantage to leaving it like that. You could multiply through, and it gets messy, ugly, but there's no reason not to leave it like that either. So, let's see how close to the answer they got. Well, they left it as 2 times 3x plus 1, which we had up there, and then they combined this denominator here to be that. So yeah, just factor out a 2 times 3x minus 1 times 3x, negative 3x squared plus 2x plus 9 all over that cube. That's exactly how they left it. They didn't multiply through here. They did 2 times 3x minus 1. But you see, and that, I say it over and over again, in calculus especially, there are so stinking many ways you can write your answer correctly. So therefore, I don't know what they do with WebAssign. They're only looking for one answer. And you have no clue whether they're going to factor out the 2 or not factor out the 2. Whether they're going to multiply all that together or not multiply it together. So, to me, that was going to cost me hours of trying to see if I can make my answer look like their answer. Now, sometimes it may be close enough I think, oh yeah, this is the same. But they don't usually show you your answer until they say, no, you're wrong, here's the correct answer. And I look at it and say, no, I was right, you know, and then I just want to slap them, you know, but I can't because they're just, yeah. And you can do this almost an infinite number of times. Now, there's nothing magical about the way we did it, but that's just how I gathered they were going to do it, except they left it, the 2 factored out. So, let's go on and erase all this. Anyone need this? Any questions before I move on? Okay. Let's see how they did it. I bet you it's going to be some weird factorization. Or, and this is the other possibility, okay, they could just take this and say 2 times this thing to the first power, right? Times the root of what's inside, and then go that way. That would be what I think I would have been tempted to try first, and that's exactly what they do. They do 2 times this thing to the first power, and minus 1, 2, minus 1 is 1, then times the root of what's in here. With the root is in here, they're going to use the quotient rule, which I would have avoided like the plague, but they're going to do it. So the quotient rule, you tell me what that's going to be. This part is just fine like it is. This is going to be low d high, which would be 3 times this thing, right? Minus high d low, that would be 2x times this thing, right? So I bet you that's what they're going to do. Let's see if that's what they did. They left out front 2 times 3x minus 1 over x plus 2, x squared plus 3, times, and there's the denominator, low times d high, 3, minus high, 3x minus 1, times d low, which is 2x, all over denominator squared, low. Okay? So, yep, that's what they did. And again, Okay, these are multiplied, so basically you just multiply this together. 2 times this, times, and then when you multiply this out, that gives you 3x squared plus 9, that's that part, minus 6x squared plus 2x, minus 6x squared plus 2x, that's that part. And then multiply your denominator, because these are products here, so just multiply them together, that's fine. So this way avoided the least common denominator way. So that's one little advantage of it, if you live with the quotient rule there. And then they left this in this form and combined like terms here, minus 3x squared plus 2x plus 9. And that's exactly what we got as an answer. So this way may have been just a little quicker. You certainly didn't have least common denominators here because these were all products. But you did have quotient rule, which you may not like or like. But it wasn't hard on this one because they're pretty simple quotients. I mean, factors there.
Why do they not use the quotient rule in the first one?
Well, you do the power rule first. You know, the chain rule says 2 times this to the first power. There's no quotient rule there until you do the derivative of this. There's where your quotient rule is. Yeah. Good deal. Good question, though. All right, that was example 9. We got the same answer either way. And let's move. Oh, yuck. Can't believe it. We're out of time already. We'll start next time with trigonometric functions in the chain rule. And we're almost through with this section. So let's give you some homework exercises here. Do any of the odds 3 through 7. They're all at calcchat.com and 3 is at calcview.com. Do any of the odds 9 through 33. They're all at calcchat.com. Only number 9's at calcview.com. And hold off the rest of those until we get those covered. 35 through 53. Let's see, what in the world is that next part about? I think you can do the odds 55 through 59. No, 55 or 57. 59 has a trig function in it. And we'll hold off and do the slope of a graph and things like that later. All right, good deal. All right, first test. Keep those coming in, folks, because after this section 2.4, we have implicit differentiation 2.5, and then I'm thinking we may just skip 2.6 because we need to be moving on. So we'll have a test then on those 5 sections. Good deal, thank you. And get those papers into me too, don't forget them. What's that? Yeah, I see, yeah, that's what reminded me. Thank you. All right, good deal.